We are going to start on lecture 5. Good afternoon. So in the last class itself, I had given a clear indication of what we are going to do in today's class. So let me start by sharing my screen. So we said in the last class itself that we are going to look at three things today. One is the speed torque characteristics of some of the practically existing system. Some practical loads. This is the first thing that we are going to look at, because unless we know clearly how load speed torque characteristics exist, or how it behaves, how a load speed torque characteristics behave, we will not be able to exactly meet the needs of that particular load. So for that purpose, we will need to analyze what kind of load systems exist in actual practice. The second thing that we are going to look at is stability. This is basically steady state stability. So let us say a particular system is working at a particular operating point, and if there is a small amount of disturbance that is occurring in the system, maybe due to a small variation in the load, maybe due to the variation in the frequency, or if there is some kind of hiccup in the coupling. So in those cases, whether the operating point would be stable, that is whether the system would return to the same operating point irrespective of the disturbance that has happened. So this can be examined by knowing the load speed torque characteristics as well as the motor speed torque characteristics. So we are going to look at that as well. And the third thing that we are going to look at is something called load equalization. So these are the three things that we are going to look at, and this should conclude our discussion on dynamics of the load system. Okay, so let us try to first of all start with the speed torque characteristics of some practical loads. So we are going to start with this. So we already talked about at least two kinds of loads. One we said as constant torque load. So irrespective of the speed at which the system is going to run, the torque posed by the load to the motor is going to be a constant. So typical examples are gravitational loads, that is the loads that are being lifted against gravitation. So typically hoist or an elevator, the lift. These are all typical examples of constant torque load, because I'm going to assume that they are moving at very small speed. So it is not going to really make any variation in G value, that is acceleration due to gravity value. So, and we are going to assume that it is in the Earth's environment that we are doing this. So these are typical examples of constant torque load. So this is going to be a constant torque load, either a hoist, which is lifting weight against gravity, or an elevator or a lift, that is going to be typically a constant torque load. Another load that we talked about was fan type load or centrifugal pump kind of load. So these are two loads which will have the load torque being proportional to omega square. Here TL is going to be a constant irrespective of speed. So we are always talking about speed torque characteristics. So this is irrespective of speed. Whereas this is going to be dependent upon speed. So the load torque is going to be proportional to omega square, which means the load power is going to be proportional to omega cube, because torque multiplied by omega is speed. Torque multiplied by omega is going to be speed. So this has to be written as TL multiplied by omega. Now there could be combinations of these torques. For example, if I am looking at an electric vehicle or a train which is moving, when you start the train, initially when it has to start moving, you are going to have quite a bit of static friction that is being faced by this particular load. After that, after the train starts rolling, the wheels start rolling, it is going to come down, right? And after that, it might actually increase as the speed increases further and further if it is a high speed train. So if I am talking about a high speed train, then it has to tear through the wind column, and then it has to progress further. So that means as it is moving at higher and higher speed, you are going to see that the torque increases further and further. So I should be able to say if this is the frictional torque, static frictional torque initially, it decreases as the wheels start rolling. And after that, it is going to increase further and further like this. So I should say this is omega axis and this is the load torque axis. So this will be the corresponding variation of the torque when you consider a high-speed train. In the same thing, if I try to plot in a similar kind of speed torque plane, if I try to plot for a constant torque load, for example, I will have the torque as a constant irrespective of the speed. So I should say this is the constant torque load characteristics. Whereas if I'm talking about fan type load, as the speed increases, the torque is going to increase as square of that. So it has to be parabolic. So I should show as though it is the parabola like this. And I have to have a parabola, not, still the torque will be positive. So that is the reason why the torque is positive, even though the speed is negative. So here the speed is going to be negative. So I'm going to have this as the load torque for a fan type load. I should write this is for fan type load. Okay. Now, if I try to look at a system, something like an elevator system in Sears Tower, for example, where we are going to have this particular elevator moving at a very high speed. So it has to again tear through the wind column and really travel at a very high speed, because if it has to reach until 112th floor within a matter of couple of minutes, then it has to really move faster. So in that case, if it is just an elevator, I would have had constant torque load characteristics somewhat like this. So I should just draw as though the load characteristics are a straight line. This is TL equal to constant. Whereas if I am looking at a parabolic characteristics, which is corresponding to fan type load, this is the kind of characteristics we are going to have. Now, this is the addition of both of them, because the elevator's weight is definitely there. There is no doubt. The people who are going to travel inside the elevator cage, their weight is already there. But on the top of that, I have to add whatever is the torque that is contributed by tearing through the wind. So I need to add these two and show it as though this is the way my complete characteristics are. So it actually gets added together. So this is TL which is actually due to the weight of the cage plus the frictional torque due to wind column. Let me call this as windage. So both of them put together is going to be the torque speed characteristics of an elevator, high speed elevator. So this is high speed elevator that we are talking about. Okay, so in which case this has to be my speed axis and this has to be my torque axis. So this is the exact way you are going to have the speed torque characteristics for a high speed elevator. There could be constant power loads, typically in a train which is actually coasting, which is just moving at a constant velocity, roughly. So in those cases, you are going to see, already it has attained kind of a steady state. So the motor has to produce only a constant amount of power. So constant power load is another type of load you may see normally. So in that case, if power is a constant, that means T multiplied by omega is a constant, which means TL is proportional to 1 by omega. This is going to be 1 by omega. So if I say this is omega, and this is the load torque, So in that case, I'm going to have something like this. So it will be a hyperbolic kind of characteristics. That's what is the characteristics for a constant power load. So there are different uh, types of loads that are encountered in real life. So we took some of them. So one is constant torque load, which is like hoist and lift, where the torque is constant irrespective of the speed. Then the other one is fan type load or centrifugal pump kind of load, where the load torque is going to be proportional to omega square. Then there could be high speed train, where initially there is a good amount of static friction, but after that it is going to decline. The torque demand is going to decline, and then it can be added to the original torque requirement of the train, which is actually in the form of a parabola, because it's a high speed train. It has to tear through the wind column. Another one we talked about was high speed elevator. Then finally, we talked about constant power load. So these are different kinds of load torques we may encounter in real life. So the next thing that we are going to talk about is stability of a drive system. And this stability is actually steady state stability of a drive system. Okay, so we are looking at steady state stability of a drive system. So in steady state stability of a drive system, let us try to first of all look at again the speed torque characteristics of the load as well as the motor. So for example, let us say this is omega and this is going to be the torque. I'm just writing torque because we are going to specify whether it is electromagnetic torque developed by the motor or it is the load torque that is actually manifested by the load or demanded by the load. So I'm going to look at, first of all, let's assume it is a three-phase induction motor. So three-phase induction motor, I'm going to have the speed torque characteristic somewhat like this. So this is the speed torque characteristics of a three-phase induction motor. So let me show this as TE. This is the electromagnetic torque that is encountered or that is developed by the induction motor. So let me draw the load characteristics. Maybe let me take a constant torque load, for example. So let me just take a constant torque load somewhat like this. So this is a constant torque load. So I should have a straight line characteristic somewhat like this. Let me probably erase this because it's not really all that neat. So let me just draw this particular thing as constant torque load. So this is TL. Now, the operating point is where we are going to have J d omega by dt, which is equal to TE minus TL. This should be 0. When this is 0, that is where you are going to have the equilibrium point obtained between the interaction. When you have an interaction between the load and motor, this is what is going to be the equilibrium point. So this equilibrium point can be achieved either here. Let me call this as point A, or it could have been achieved here, which is actually point B. So let me try to examine the stability corresponding to points A and B. So let us say there is probably a little bit of variation in the frequency. Maybe the frequency has decreased slightly in the grid, because of which I'm going to have a little bit of reduction in the speed. So let us say at point A, when the motor is operating or when the system is operating, let there be a small reduction in the frequency. So obviously I'm going to have the speed decreases slightly, which means it is going to become omega minus delta omega. This is going to be the variation in the speed. When there is a slight variation in the speed, now let us see what happens to the electromagnetic torque value and what happens to the load torque. So very clearly it's a constant load torque characteristic. So TL is a constant. Even if the speed changes, TL will not change. But if I try to look at what is the electromagnetic torque value, when I am trying to look at the speed slightly changing, I will have a slight increase in the torque. The torque would have increased by a quantity which is corresponding to delta TE. So there is going to be a slight increase. So TE is going to increase slightly. So when TE increases slightly, now TL remains the same, whereas TE has increased slightly. So TE minus TL is going to be delta TE, which is a positive quantity. So this is going to be a positive quantity. So if I am going to get a positive quantity, which is going to act like an accelerating torque, then d omega by dt will be positive. So there will be an increase in the speed. If there is an increase in the speed, this is the direction in which the operating point will travel. So from here, slowly it is going to travel towards A. So from A, it had moved away from A towards reduced speed direction, but now it is going to increase slightly because the speed has increased now slightly. The electromagnetic torque will get decreased to the original value, which will exactly balance with that of TL. So it will get back to point A and stay put there. So point A is termed as stable point, or it is steady state stable, because even if there is a small disturbance, that disturbance will cause the difference between TE and TL to reach such a value that it will drive it back to the original point A itself. So that is why it is stable point. On the other hand, let us try to look at point B. Let us say at point B, we are going to have probably a slight reduction in the frequency again. So at point B, if we again put forth similar argument, and if we say if there is a slight increase in the speed, because increase in frequency is the root cause probably. So if there is a slight increase in speed, then what is going to happen is increase in speed is essentially in this direction. So when there is an increase in speed, you're also going to have an increase in the torque. The torque value also increases. So you're going to have this as delta TE in this particular case. So you have an increase in the torque when there is an increase in speed in point B. So increase in speed will cause an increase in TE. Okay. So increase in speed will cause an increase in TE. But TL is a constant. So if I look at what is TE minus TL, TE minus TL, this is going to be again delta TE, which is going to be a positive quantity. So if this is a positive quantity, which is corresponding to J d omega by dt, obviously I'm going to have a positive d omega by dt, which means speed will increase further. So if speed increases further, the operating point is going to move away from B. It will not move towards B, rather operating point will move away from B. So which means point B is not going to be retraced once again. It is not, the operating point is not going to return to B once again, which means point B happens to be an unstable point. So point B is an unstable point because if there is a disturbance, immediately the operating point is going to be completely disturbed and the system is going to move away. So in this particular case, that is how the induction motor starting happens. And then ultimately it settles wherever the load torque is equal to the electromagnetic torque itself. So that's why generally in the induction motor, we always call this portion from torque equal to 0 to torque equal to T max point. This we call as stable operating characteristics, whereas when we look at Tmax to the starting omega equal to 0, we call this as unstable operating characteristics. So this portion is generally going to be stable operating characteristics, whereas this portion is going to be unstable as far as an induction motor is concerned. But again, the stability or instability is not only dependent upon electromagnetic torque. It also depends upon what kind of load torque I am actually visualizing in along with the electromagnetic torque of the motor. For example, even if I am having a characteristics of the induction motor somewhat like this, if we have a fan type load probably which is intersecting with this end of this induction motor characteristics, which is normally called unstable, you may have stable operating point coming up even here. This point B may be even a stable operating point if this is a fan type load. So you need to examine clearly how the load interacts with the motor, which is working along, which is coupled to the load itself. So depending upon that, you can say whether a particular characteristics is going to be stable or unstable, whether a particular operating point is going to be stable operating point in steady state or not. So this can be mathematically explained as well. So let us try to give a mathematical explanation for steady state stability. So if we are looking at a mathematical explanation, let us first of all write the original equation, which is TE minus TL equal to J d omega by dt. And let's say if there is a small disturbance in the speed, which is corresponding to delta omega. So when the speed changes by a value of delta omega, I should be able to write this as J d omega plus delta omega by dt equal to TE of omega plus delta omega minus TL of omega plus delta omega. But I can say maybe TE changes when omega changes from omega to delta omega plus delta omega. Maybe the incremental change in electromagnetic torque will be dTe by d omega multiplied by delta omega. This is the variation in TE when the speed is disturbed by a magnitude of delta omega. The same way I can say variation in TL, that is also going to be dTL divided by d omega multiplied by delta omega. So when I compare equation number 1 with equation number 2, along with all these expressions for TE and TL, that is whatever is the delta TL, and this is going to be delta TE. So I should be able to write this as TE plus delta TE minus TL plus delta TL. I should be able to write like this. So this is equation number 2. This is equation number 2. So when 1 is subtracted from 2, I should be able to write this as J d delta omega divided by dt. So let me write this as J d delta omega by dt. Okay, that should be equal to d TE divided by d omega multiplied by delta omega, right? And I should be able to write this other one as minus dTL divided by d omega multiplied by delta omega. Okay, so I can write this like a first order differential equation in delta omega. So I should say J of d delta omega by dt. And I can write this, the entire thing can be brought to the other side. So I should be able to write this as dTL divided by d omega minus dTe divided by d omega multiplied by delta omega equal to 0. So this is a first order differential equation in terms of delta omega. So I should be able to write the expression for delta omega as whatever is the initial disturbance I have got in the speed, delta omega naught multiplied by 1 e power. So I should, the solution for this should be in terms of exponential. So e power j minus 1 by j multiplied by dTL by d omega minus dTE by d omega. It is very, very similar to writing Li plus R, L di by dt plus Ri equal to maybe some voltage source or something like that. Or if there is no excitation, only there is initial current that is built up in the inductance, or there is a stored energy in the inductance, I can write this as equal to 0. So for this, generally we will write the solution as I of t equal to I, whatever is the initial condition, multiplied by e power minus t divided by tau. Tau is L by R, so this is going to be R, and this side is R. TR by L. This is going to be the solution normally we write for this kind of first order transient circuit. The same thing holds good here also. So this is essentially minus 1 by j multiplied by dTL by d omega minus dTE by d omega. And that has to be multiplied by t, of course. I have to, because this is the time constant in one sense, so multiplied by t. So if the disturbance has to die down, when t really reaches infinity, delta omega should be 0. So at t equal to infinity, delta omega should be 0 if the system has to be stable. So if I want this to be 0 at t equal to infinity, I should say this entire term, this should be actually positive. Only then e power minus infinity will literally become 0. So for the disturbance to die down, we should have dTL by d omega minus dTE by d omega to be positive. This should be positive. That means I have to have dTL by d omega should be greater than dTE by d omega. So this is the condition that has to be adhered to for steady state stability. If the rate of increase in the load torque with respect to speed is higher than the rate of increase in the electromagnetic torque with respect to speed, we will not have much of acceleration further possible. So obviously this particular point is going to be stable. So we'll take a couple of systems where we want to examine the stability. So let me just take two characteristics arbitrarily. So let us say this is omega and this is TE. So let me just draw this as the electromagnetic torque, and let me just draw this as the load torque. So I have just shown two characteristics, and let me call this operating point as P. So we want to check whether P is stable. Qualitatively, we should be able to examine this. For qualitatively examining this, let me just assume there is a small disturbance in the speed. So maybe there is an increase in the speed. So if there is an increase in the speed, if I look at what is the kind of torque we have, the load torque, if there is an increase in the speed, I'm going to have a load torque to be increasing. So TL increases if delta omega is positive. Whereas if I try to look at the same increase in the speed, so this is the speed. So now if I try to extrapolate this towards the speed axis, very clearly my torque has decreased. So I'm going to have TE decreases if delta omega is positive. So if the speed has increased, I can see that compared to what I had as TL, this is delta TL, whereas this is going to be delta TE, which is actually in the negative direction. So obviously, I'm going to have here dTE by d omega is negative, whereas dTL by d omega is positive. So I'm going to have dTL by d omega greater than dTE by d omega. So this system will be stable. On the other hand, if I am going to look at a characteristics somewhat like this is probably the TE characteristics. Whereas I'm going to take something like this as the load characteristic. So which is a constant load torque. So let me take this as the constant load torque. Let me again redraw this. So I'm going to say that this is actually the electromagnetic torque characteristics, whereas I'm going to have this as the load torque characteristics. So if I try to look at this way, and let us say this is a constant load torque. I have not really drawn it that way, but assume it's a constant load torque. So I'm going to have dTL divided by d omega equal to 0. It's not going to change at all. So this is for point Q. So we are talking with respect to point P here, whereas we are talking with respect to point Q here. So dTL by d omega is 0, whereas here very clearly as you increase the speed, so increasing the speed is in this direction. The torque also increases. Actually, it goes from more negative value. Here is more negative value. It is going to less negative value. So I'm going to have in point Q, dTE by d omega is going to be positive. So we will have very clearly point Q is unstable, because we are having dTE by d omega is greater than dTL by d omega. So this is definitely an unstable operating point. You can check this qualitatively also, and it will turn out to be an unstable operating point. That means if there is a disturbance, you're not going to come back to the same point. Rather than that, you're going to move away from the normal operating point. So which means it is unstable. Okay. So the third point that we are going to discuss today is regarding load equalization. So where is load equalization really used? So let us assume probably there is something like a cutting machine, where probably you are going to have a particular cutter which is coming down heavily on a material which is going to be cut. So this is going to slice this into two pieces. So after this piece is sliced, the next piece is going to slowly move and occupy this position. So this is going to happen one after another. So whenever the cutter is really, working on the piece, only then you're going to have a heavy load torque. Whereas when this particular piece has to move and occupy the position of the previous piece, all that along, this particular cutting apparatus is not going to be loaded at all. So load torque, if you try to look at it in a cutting machine, for example, you might see that it is at a very high value for a very short while when it is cutting. and after that it is going to be at a very low value for a long duration. Then again it is going to increase to a high value. Then again it will come down to a low value and so on. So with respect to time, if I plot the load torque, this is the way the load torque is going to manifest itself. So let me call this as TL max and let me call this as TL minimum. And if I'm going to employ a motor which is capable of developing TL max, we are going to actually underutilize the machine because that machine will be utilized to its fullest capacity only for a very, very short duration. This short duration, let me call as TH, that is heavy load duration, and let me call this duration as TL, which is the light load duration. So I'm going to have the light load duration for long, whereas heavy load duration is going to be for a short while. So the motor will not be utilized to a large extent at all. So if I am able to store the energy during this light load period in some kind of arrangement, something like a flywheel, then I should be able to release that energy from the flywheel to the load when the load is really coming down heavily on the drive system. So whenever there is going to be a higher amount of torque available, as per our equation, J d omega by dt is going to be equal to TE minus TL. So if the motor is developing a higher torque than what is needed by the load system, in that case, the speed will increase. Whereas if the electromagnetic torque developed is smaller, like in this duration, in TH duration, we are going to have definitely speed decreasing. So you might see that the speed falls rapidly during this time and it increases during this time and again it falls and then it increases and so on. So this is going to be the variation of speed, how the speed varies during this kind of operation. Whereas if I try to look at what kind of torque the machine will produce, so let me draw the torque here. So during this duration when the speed is falling, right, slowly the machine's torque is going to increase. And during the other duration where the speed is rising, you are going to see that the machine's torque is going to fall. So this is going to happen repeatedly. So this is going to be TE, which is developed by the motor, whereas this is TL max, and this is going to be TL minimum. So let me call this as TE max, and let me call this as TE minimum. Okay, so the electromagnetic torque of the motor varies only from TE max to TE minimum, whereas the load torque varies over a wider range, which is TL max to TL minimum. So a flywheel can be employed. So a flywheel is basically another wheel, which is heavy duty wheel, which will also rotate along with the motor shaft. And because it has a very heavy weight, half J omega square of the flywheel is going to be quite high because the moment of inertia of the flywheel itself is going to be high. So the kinetic energy stored in the flywheel is going to impart its energy to the load mechanism whenever there is a shortfall in the torque developed by the motor. So essentially it will be somewhat like this. If this is the motor, and let us say this is the load to which the motor is imparting power. So this is the shaft which is coupling these two. So in between, I'm going to employ a large flywheel. So the flywheel I can show in the elevation, it is somewhat like this. So this is going to be a flywheel. But in actual practice, if you see a flywheel, the flywheel is going to be like a big wheel, which is having again spokes, which are pretty thick. So this is the flywheel. So this is going to be really big and heavy. And that is the reason why it is able to manage the shortfall or excess in the torque. So how do I determine the size and moment of inertia of the flywheel if I know what is the maximum load torque and minimum load torque, and what is the maximum electromagnetic torque that can be produced by my motor, and what is the minimum electromagnetic torque that is being produced. And if I know for how long the high load torque is going to come on the shaft. And also I should know how much of speed variation my entire mechanism can tolerate, because the speed is now varying from omega minimum to omega maximum. So the speed is going to again change from omega minimum to omega maximum. So how am I going to really look at these kinds of variations? And for this kind of allowable variation, how am I going to design a flywheel? This is the question at hand. So for equalizing, for rather limiting, I should say for limiting the electromagnetic torque variation from TE max to TE minimum, and also to limit the speed variation from omega minimum to omega maximum when the load torque remains at TL max for TH seconds and TL minimum for TL seconds. What should be the moment of inertia of the flywheel? This is what we are looking at. Okay, so this is what we are going to solve for. So let us try to do the mathematical derivation for this. So we are looking at load variation very clearly from TL max to TL minimum. So TL max persists for TH seconds and TL minimum persists for TL seconds. Okay. So let me first of all say that maybe my motor has a characteristic somewhat like this. In most of the cases, whether it is a separately excited DC motor or induction motor or all these things, this is going to be the kind of characteristics we are going to have for the motor. So this is omega and this is going to be TE. So if I am looking at the no load condition speed, this is going to be omega naught. Whereas if I am looking at rated condition at which it is developing rated torque, so under that condition, I am going to have the speed to be something like omega r. So the speed would have fallen by from omega naught to omega r. Omega naught is the no load speed, omega r is the rated speed. So I should be able to write the torque at any other point in between these two. If I say that this is the torque at any other point, I should be able to write this as the speed at this particular point, let me call as omega. Let me call this as omega. So omega should be equal to omega naught minus whatever is the slope of this line, which is omega naught minus omega r divided by TR. This has to be multiplied by T. So this will actually give me the speed at a torque of T. So this is going to be the speed of the motor at a torque of T when the motor is delivering a torque of T. So now I should be able to write this as d omega divided by dt is equal to, this is a constant. So I should be able to write this as minus dt divided by dt. So let me write this as electromagnetic torque. So dTe by dt multiplied by omega naught minus omega r divided by tr. Okay. Now if I try to multiply this by j, let me multiply this by j on either side. Okay. So I should be able to write this as j d omega by dt equal to this dte by dt multiplied by j multiplied by omega naught minus omega r by tr. But j d omega by dt we know is te minus tl. This is the original equation we have always written for the mechanical system. So if I try to call this entire quantity as mechanical time constant tau m, I should be able to write this as tau m multiplied by dte divided by dt plus te equal to TL. So this is a first order differential equation in electromagnetic torque. So we should be able to calculate the electromagnetic torque if we are given the mechanical time constant and the load torque at that instant. Okay. So let me again draw the variation what we had drawn earlier. I am talking about this as the load torque variation. This is from TL max, then it goes to TL minimum, and again it goes to TL max and so on. So this is with respect to time, and this is going to be TL max, and this is going to be TL minimum. Okay. Now at the same time, if I try to look at the electromagnetic torque, we already drew this if you may recall. Electromagnetic torque is slowly increasing here, then it is going to decrease here, and again it will increase and it will decrease and so on. So this is going to be TE max and this is going to be TE minimum. Now this is a first order differential equation, so we should be able to write the solution clearly for this. We should be able to write the solution as TE of t with respect to time. That is going to be whatever is the steady state torque it might achieve multiplied by 1 minus e power minus t by tau m plus whatever is the initial torque it had multiplied by e power minus t by tau m. Again, I'm writing the solution from the original equation what we wrote, Ri plus L di by dt is equal to some VDC. For this, generally we write the solution as I of t is equal to first order differential equation solution, which is going to be the steady state current VDC by R multiplied by 1 minus e power minus t by tau, plus if there had been an initial current, I initial multiplied by e power minus t by tau, where tau is equal to L by R. This is the time constant. So the same kind of solution we are going to get for the electromagnetic torque also here. So the duration for which heavy load is applied is TH, for which the light load is applied is TL. So I have TH and TL. So now I should be able to write this corresponding to, if I just start from 0 and I reach until TH, if I had allowed this particular high load for infinite amount of duration, hopefully the motor should have reached TL max in steady state. So for the duration TH, for the duration TH, if I try to write the solution, I should say TE of TH at the end of TH, which is actually TE max. That is going to be equal to the steady state torque would have been TL max multiplied by 1 minus e power minus TH divided by tau m. Plus, what was the initial torque? The initial torque would have been TE minimum because it is going from TE minimum to TE maximum. So, TE minimum multiplied by e power minus TH by tau m. So, please note that this point is TE minimum and this point is TE maximum. So TE maximum is equal to TL max multiplied by 1 power e power minus TH by tau m and TE minimum multiplied by e power minus TH by tau m. So I'm going to have basically in this particular case, I can take this TE max to the other side. So I can say TL max minus TE max. Okay. And I'm going to say this e power minus TH by tau m, that is existing still. So I should be able to write this as TL max multiplied by minus of e power minus TH by tau m. And if I take it to the other side, I should be able to make it as positive. So this is equal to TL max minus TE minimum multiplied by e power minus TH by tau m. So I should be able to write this as e power minus TH by tau m equal to TL max minus TE max divided by TL max minus TE minimum. So I should be able to write this as e power TH divided by tau m is reciprocal of this. So this will be TL max minus TE minimum divided by TL max minus TE maximum. Okay. Now let me take natural logarithm on both the sides. So I should be able to write this as TH divided by tau m equal to natural logarithm of TL max minus TE minimum divided by TL max minus TE maximum. Now from this, I should be able to say tau m, which happens to be J multiplied by omega naught R minus omega naught R divided by TR. So I should be able to write this as J multiplied by omega naught minus omega R divided by TR. That should be equal to TH divided by natural logarithm of TL max minus TE minimum divided by TL max minus TE maximum. So if I know what is the maximum torque that can be developed by my motor, and if I know the characteristics of the motor, which will give me omega naught, omega R and TR, And if I know what are all the maximum load torque and minimum load torque, and for how long a duration the maximum load torque is applied, I should be able to calculate the moment of inertia of the flywheel that I need to employ so that my drive system adheres to all these conditions. Okay. A similar derivation should be possible. This what we have done is for duration of TH. A similar derivation can be done for TL duration. Please do it yourself. I'll just give only the result. So the result that is corresponding to the TL duration is again tau m, which is equal to J times omega naught minus omega r divided by TR. That will be equal to TL. This is corresponding to light load condition duration. So this is TL divided by natural logarithm of TE max minus TL minimum divided by TE minimum minus TL minimum. Okay. So these are the two expressions. One is based on light load duration. The other one is based on heavy load duration. So these two expressions will, or one of these two expressions will allow us to calculate exactly the moment of inertia of the flywheel, which is needed for maintaining the electromagnetic torque developed by the motor within TE max and the speed variation within a certain interval for heavy load being applied for a duration of TH and light load being applied for a duration of TL, where the variation between heavy load and light load is very, very large. Okay. So based on this expression, we will do a problem tomorrow. So we would be doing the problem in the next class, but please do the derivation corresponding to the light load condition as well, which I have not done. Okay. So we will meet in the next class.